Hi everyone, welcome to this channel, your merchant, the merchant construct-preneurs and tutors, your go-to channel for everything about construction engineering, structural engineering. So today we'll be looking at a very important topic, and this topic is about how to design a cantilever retaining wall. This is for beginners, young engineers and professionals alike. So most people have not been opportune to actually work on a retaining wall. Some people have not even designed it before, and they were wondering how they come about these massive structures and how it is stable and everything. So in this video you're going to learn how to design this retaining wall. This is the structure of a retaining wall. Cantilever retaining wall has a stem, it has a base slab where the front of the wall is the toe, the back of the wall is the heel, and so you design it against overturning, against sliding, and against soil bearing pressure. You ensure that the bearing pressure is adequate enough to carry the retaining wall, while the retaining wall is meant to retain earth between two different surfaces or two different levels, right? So let's go straight. Now, what is the retaining wall? The retaining wall is a structural element designed to hold back soil or other materials at two different ground levels. It prevents soil from sliding, erosion, or collapse when there is a change in elevation. So as you can see from these images here, you can see this is the soil here on this level, and this is the second level. So this is a retaining wall, and this type of retaining wall is a sheet pile retaining wall. It is designed or provided to hold back soil between two different levels. As you can see here, this line shows one level, this line shows the other level. This line shows one level, this shows another level. So the retaining wall is there to prevent sliding, erosion, or collapse when there's change in level. So the retaining wall are commonly used in road construction, building basements, slope sites or hilly terrains, bridge approaches, and embankments. So there are various uses for retaining wall, right? So the primary role of a retaining wall is to resist lateral earth pressure exerted by the retained soil and safely transfer these forces to the ground. So this soil behind this, it's resisted because this soil now is trying to push it horizontally to make it collapse, right? So it's try to resist that pressure and then ensure that it safely transfers the load of this, or the forces of this soil behind it, safely to the ground. So these are different types of retaining walls. You have the sheet pile retaining wall, you have the gravity retaining wall, we have the cantilever retaining wall, we have the counterfort retaining wall. So the difference between the cantilever and the counterfort is that the counterfort is no longer a cantilever because it's not behaving like a cantilever now. It has extra support called the counterfort behind the wall at the where you have the heel, right? So our main focus is the cantilever retaining wall. So now, what is the cantilever retaining wall? The cantilever retaining wall is a reinforced concrete wall that consists of a vertical stem, a base slab divided into the heel, which is behind the backfill, and the toe in front of the wall. That's as I illustrated in the image, my first image there. So we have, this is the toe, the shortest part, the heel, this is it, and the total heel and toe is the base slab, and then this is the vertical stem, this is the stem, right? So the behavior of the cantilever retaining wall, so the wall acts as a cantilever fixed at the base, right, with the stem resisting the lateral earth pressure from the soil. So this explanation is giving us this, how this image is showing how this behaves. The soil is acting based on the weight is acting on the base of the cantilever of the retaining wall. The soil is also exerting horizontal pressure on the wall, causing it to deflect like this, in this shape. The base is also in this shape. Now the soil, underlying soil, is trying to raise the toe in this portion here. So you can see this reinforcement. So once you want to reinforce, you reinforce it along this line. You can see along this face, so that once this pressure is trying to force it, it's not going to bend it. So this reinforcement is going to prevent it. The same thing on this portion now is deflecting like this. So your reinforcement is at the top here, like the face of the soil. Then at this portion here, your reinforcement is also at this portion here. So while this one is extended to the end, the reinforcement is also here, so that it's preventing it from overturning, right? So as you can see, the deflected shape of the wall, the horizontal pressure, the vertical pressure, the deflected base shape at the base, right? So the stability of the retaining wall is achieved through the combination of its self-weight and the weight of the soil resting on the heel slab. These forces counteract the overturning and sliding effects caused by earth pressure. So proper design ensures the retaining wall is safe against overturning, against sliding, against bearing failure. It's overturning, sliding, bearing pressure, and then structural bending. While adequate drainage, this is key. Adequate drainage is provided to prevent water buildup behind the wall, because once water is built up, the pressure increases. So it's no longer about the pressure of the soil. Now water already added to it, and then if you don't drain this properly, you're going to have serious problems, right? So the first step is preliminary design. That's the first step. So this preliminary design dimensioning is to get a range of dimensions for different elements to be sure that we are not coming to do massive over redesigning, right? We don't just assume dimensions. We need to know what we need. So the first is minimum embedment depth, and this minimum embedded depth is the depth at which this retaining wall is buried to the ground based on the level from the face. So this is the minimum embedded depth, HM. It's given by this formula. This Q naught is safe bearing capacity of the soil. This is the unit weight of soil, given by this formula. So once you calculate this, you have this 0.925 approximately 1 meter. So that's the reason why I have it as 1 meter here, right? Now the next one is overall height of the retaining wall. The overall height is now minimum embedment depth, then from that level to the top of the earth you want to retain, and that is it. So 4.5. So when you add these two together, you have it as 5.5. You can see the dimension here. So overall depth, base depth or base width, sorry, this is the base, the width, overall width of it is given between this 0.4 h to 0.7 h. So we are using 0.7 h, and it's given by this. When you calculate it, will give you this 3.8 meters. So the base thickness is still between 0.1 h to 0.067 h. So when we use 0.067 h, we have this value, so we are using 0.3. Same thing here, 0.15 multiplied by 3.8. So at this portion here, we have it as 0.6. This is not correct. This is not correct. It's not correct. So 0.6 meters. So stem thickness is this, given as this. We use 0.3. The heel. Now, as I said, this is the stem. This is the toe. This is the heel. And the total of this is the base. So once you do this minimum or this preliminary dimension, to guide you on what is required and expected, right? Okay. Now, so the next step is calculate the pressure coefficients and the pressure. So the first one is coefficient of active pressure. It's given by this formula. We have it as 0.03, right? 0.33. Coefficient of passive pressure is given by this formula, Kp. You have it as 3.0. Then active pressure is this. This is the formula, right? Passive pressure, this is the formula. As you can see, active pressure is the pressure on the heel side of it, and this is the pressure diagram. This triangle is the pressure diagram. This rectangle is the pressure diagram of the surcharge, the soil on top of the backfill material here. And then this portion is the pressure diagram of the soil in front of the toe. So that's why we have active pressure, we have passive pressure, we have surcharge pressure. So each of them have their formulas behind it. So you have coefficient of active pressure multiplied by unit weight of soil multiplied by the height of the earth retained. You can see for here H, you can see this is it, Ka times Q. Q is the surcharge. You can see the legend here. Q is the surcharge. Then okay, so that is it. So move on to the next. Now step 3 is to calculate the horizontal and vertical forces. We have the resultant horizontal force, we have the resultant vertical force. As I said, or as I was explaining, now the stability of the retaining wall is based on two forces, the horizontal forces and the vertical forces. Now the vertical forces include that of the self weight of the retaining wall, which include the stem, the base, right? And then any other thing that is on top. Now the soil is exerting two forces, horizontal force and vertical force, and that vertical is the weight of the soil on the what's the name, on the base, on the hill side, on the toe side, still on the base, right? Then for the horizontal pressure, you can see is that one is acting on the stem, that of the soil on the hill. This is the surcharge, and then for this is for the soil in front of the soil. So the stability is based on these forces, trying to balance these things together, right? So let's take it one after the other. Active force, that's on the active side there, Fa, is given as the shape of this triangle. This is a triangle, so the area of this triangle is half base times height. So half multiplied by active pressure base times the height of this is the height here, right? So you get this value. For the passive force, the same thing at this portion. This is a triangle, so half times base times the height, 1 meter height. Then the surcharge force, this is the rectangle, so area of a rectangle is what? Base times height. So the resultant horizontal force is active force plus surcharge force minus passive, right? They are not going in the same direction, they are acting in different direction on the retaining wall. Now for the resultant vertical force, we have the weight of the stem, we have the weight of the base, we have the weight of the active soil, we have the weight of the passive of the soil, passive soil. So the weight of the stem is given by what? The width multiplied by the height and unit weight of concrete. So the width of this stem multiplied by the height by the unit weight of concrete. So you get this expressed in kilonewton per meter. Weight of the base, the same thing, thickness of the base times the width multiplied by unit weight of concrete. For the weight of the backfill soil, the width multiplied by the height multiplied by unit weight of soil, right? This is the portion here. The width multiplied by the height times unit weight of soil, that is 18. Same thing here, the width multiplied by the height multiplied by the unit weight of soil. So when you add, everything is acting in the same direction downward, so you add them together, you have this value here. So the next step is to carry out stability checks. Now the stability checks, there are different things to consider when considering a stability check. So the first is what? To check for overturning. Now to check for overturning, it is given by the factor of safety against overturning. Restoring moment divided by overturning moment must be greater than or equals to 2. That is the condition to be sure that you have checked this, that the factor of safety anyone is safe against overturning. Restoring moment divided by overturning moment must be greater than or equals to 2. Now, so taking moment about the tip of the retaining wall toe. Now this is the tip of it. So let me use a pen so that we will see. This is the tip here. Let me use a thicker one. So we are this is the tip here. So we are taking moment about this point here. So everything is referencing here. So for the restoring moment is the one that is trying to keep it in position, keep it in place. Those ones are acting on the base. So first one is the weight of the stem weight of the stem, we are taking our our moment to the tip here, and the distance, if you add it, this is 0.6 plus half of 0.3. So if you add 0.6 plus half of this, will give you 0.75. That's what I've calculated here, right? So this multiplied by this is what we are having here. As you can see, that is it there. The weight of the base multiplied by 1.9. So the 1.9, the base is 3.8. So half of 3.8 to the tip here is 1.9. That's why we have it as 1.9. I didn't want to start writing the 3 distance, so that is what we have here, right? So the next one is weight of the soil. The weight of the soil, this is the point is acting, and you see this one is acting this way. Okay, so weight of the soil is we half of this, and you know this is 2.9. half of 2.9 plus 0.9. So that's how we arrive at this 2.35. Same thing for this other part here. This is 0.6. So half of it to the tip here is 0.3. That's how you're able to arrive at this. And then the passive pressure is trying to restore it, because these ones are exerting this pressure in this direction. See, they are exerting the pressure in this direction, right? So we are trying to ensure that the pressure that is supposed to exert is actually restoring it back. So this one is also part of the restoring forces. So we now have it as what? So we have it as this multiplied by 0.333. This is the tip here. So this force multiplied by the height, and the height to the tip is 1/3 h min. That we have. That's the reason why we have it as this. I hope you understand. So when we break down this and calculate, we have this value. Right? So sum of overturning moments. So those moments that are trying to turn it our way. So this is it here. FA and FS. So FA to the tip multiplied by 1/3 h. FS2, half of it is coming here, and this is how this to stabilize the triangle like this. 1/3 is coming to this part, and then this other portion is 2/3. 2/3 h. So that is what this portion is. I hope this, yeah. So this 2/3 h, to such a way that once you add these two together, you get h. So the same thing here. This is how we arrive at this. So when you add all these things together, multiply and add together, you get this value. So factor of safety over overturning, we said it is restoring moment divided by overturning moment. This is the value. So 3.84 is greater than 2.0. So the retaining wall is safe against overturning. I hope this is clear. So if it's not clear, you need to go back and watch this video again, or watch this part again. So the step 5 is to carry out stability checks, continuation, and then the next one is the sliding check. And sliding check, the factor of safety against sliding is given by soil coefficient multiplied by vertical forces divided by sum of horizontal forces, and this we have calculated before, the sum of vertical forces and sum of horizontal forces, and the coefficient of soil is given by 0.5. So once we multiply this and divide it by the sum of horizontal forces, we have 2.39, which is greater than 1.5. So since we have this value, the retaining wall is safe against sliding. I hope this is clear. Now, these values we had already calculated them before. These values we had calculated them before. The sum of horizontal forces, sum of vertical forces, and then you need coefficient of friction of the soil, right? So next one is the last stability check is soil bearing capacity check. And ensure that the bearing pressure from the retaining wall is less than the soil bearing capacity. Right? So what we're saying is what the soil can carry. We ensure that the weight coming on the retaining wall is not greater than what the soil can carry. If not, it's going to sink, and then that is a type of failure. It's going to collapse. So this now is the formula is actually broken down. So first we need to calculate the centroid, and the centroid is given by the summation of restoring moments minus summation of overturning moment divided by the summation of sum of vertical forces. So that you have calculated the centroid as 1.57. Now to get the eccentricity, do the same thing. The base width, the width of the base divided by 2 minus the centroid. After that, the eccentricity is given, we got it at 0.33. Now the applied pressure, we have the minimum and the maximum, and it's given by this formula: summation of vertical forces divided by the base width multiplied by 1 plus or minus 6 times the eccentricity divided by the base width. So this plus or minus is for the minimum pressure, and then plus is for the maximum pressure of the retaining wall. So when we calculated this, we got our minimum pressure as 43.33 kilonewton per meter square, which is greater than 0, and the maximum pressure as 137.62, which is less than 150 kilonewton per meter square. So with this, we are, if it is not satisfied that the retaining wall is not exceeding the soil bearing capacity, and it is sufficient, the dimensions are sufficient for the width, for the stem, for the base, toe, heel, and every other dimension that we have assumed from our preliminary checks, right? So this is all about the stability check for cantilever retaining wall. Remember, we have different types of retaining wall. We have the counterfort. Counterfort also has its own unique calculations in ensuring the stability. Now, I think in my next video I'm going to design the reinforcement part, because this is just to check. Now we need to know what reinforcement we need for the next to ensure that this retaining wall is safe based on the stability checks we have done. What reinforcement is required for the stem, what reinforcement is required for the base, the heel, and the toe part of it, right? So thank you for watching this video. I believe we got value from all this, right? In case there are any questions, you can drop it in the comment section. I'm going to respond to them as quickly as possible, right? For more educative content on construction and structural engineering, kindly hit the like button, subscribe, and share this content to all your friends. Thank you very much. See you in the next video. Bye.